Mm. All right, so thanks everybody for joining me after lunch. I'll try to be exciting and help you, get out of the food coma that you get into after lunch. And as my title suggests, I'm going to be talking about recent developments in infrared instrumentation. And really, I'm going to be trying to tell a story about how infrared detectors specifically got developed and how they're being used to push astronomy forward. And for that reason, I like to have this as kind of the subtitle to the talk: how far we've come and how far we have to go. And this story is going to kind of parallel astronomy, because in astronomy, instrumentation is what leads us to getting these answers to the questions that we want to ask. And these questions start off really basic. Questions like, where are we? And this is where I'm going to ask you to get a little bit interactive. So if you had to describe where you are, what would you say? And you can just yell out stuff. Texas, that's good. Where's Texas?
Earth.
Earth, good. Where's Earth?
Solar system.
Solar system, yes. Where's the solar system? It's in the Milky Way galaxy. Where's the Milky Way galaxy?
Universe.
Hey, local group, yes. It's also in the universe. Where's the local group? Yeah, there's a supercluster. Yeah, so that was very easy. If you've ever taken, intro astronomy, where a good student, you have a good idea of like what our kind of cosmic address is. But knowing our cosmic address is only the beginning of astronomy. If this was the end, we could all just, pack up our bags, pat ourselves in the back and say, we solved astronomy. We know exactly where we are. But of course, all of these incremental questions only spur more complicated and interesting questions. And these questions start off as simple and complicated as something like, how does a planet form? Or what is a planet? We've heard a little bit about that earlier today. These questions talk about star formation. How do stars form? And if you want to go the next level of complexity up, well, you have galaxies, which are just these conglomeration of stars. How do these galaxies form and how do they change over time? These are all kind of fundamentally questions that we want to address in astronomy. And to do that, we have to look at the sky. Here in astronomy, all we have to work on is the electromagnetic radiation that we have from objects. And this is key to examining these objects and then figuring out how they fit into our physical model for the universe. So in astronomy, the sky, here the Milky Way, at least shown here, is the laboratory. And the tools that we use in our lab are the telescopes. And what we're trying to measure are the photons. Now, given the recent news of the electromagnetic follow-up for the neutron star merger that had this gravitational wave signature, I have to add in that gravitational waves are also very important in doing astronomy. And the follow-up at all wavelengths of this object and this detection is a really good example on how instrumentation at all scales and at all wavelengths and with multiple messengers can really, all fit together and strike science gold, if you'll pardon the pun there. So we can always use all the data we can get. But in this talk, I'm still going to focus on mostly infrared and mostly infrared detectors. So why the infrared? We're all very familiar with visible light. We interact with it actively on a day-to-day basis because that's the light that our eyes have become more sensitive to. But the infrared is really nice because it has certain key properties, and one of those really cool properties is that it traces cool objects that we're interested in learning more about, like the stars and planets. Originally in this slide, I actually used the term warm because if you think about the discovery of infrared radiation by Sir William Herschel, it really became detected as this unseen radiation from looking at a dispersed spectrum of the sun on this chemically treated paper. And he discovered also by painting different colored light bulbs and light sources black that there was this unseen radiation that seemed to be associated with heat using these thermometers. But of course, in astronomy, warm means something completely different to us. When I say cool here, I'm talking about objects that are tens to thousands of degrees Kelvin. This is where things start to get interesting in an infrared, and it just so turns out that those are where a lot of the interesting things that we want to learn about in astronomy also lie. In particular, we'll focus on stars. You probably all know William Herschel, but I was actually surprised to learn about this fellow named William Huggins, who was actually one of the first people to look at stars with a thermopile, which you guys may not know what a thermopile is. The easy and tongue-in-cheek explanation of a thermopile would be that it's a pile of thermocouples. It's actually an array of thermocouples set up so that you can measure the voltage differences across these dissimilar metals and detect these very minor temperature changes. And what Huggins actually did is use this thermopile instrument to measure the heat from two very famous stars. You may notice one of these stars, Arcturus, you're all familiar with, and Alpha Lyrae, which is actually Vega. And what's really cool is that this happened in 1869. What he was able to do was to measure the heat of Arcturus as, in these slightly archaic units, a 3-inch cube of boiling water at 400 yards was the heat from Arcturus. He measured that from a star like Vega, you have a similar cube, but it seemed to have the flux of an object that's 600 yards away. And even though that's in very convoluted units to us right now, it actually shows something really important that we all kind of take for granted is very obvious. Arcturus is a cooler K-star, so all of its radiation is going to be shifted to the longer wavelengths in the infrared. So of course it would have a stronger flux than Vega, which is an A-star that's going to have more of its flux shifted to the shorter wavelengths. So this was kind of the beginning of using infrared detectors by measuring heat from objects. But now, regularly, we get spectra of stars and spectra of stars integrated to form galaxies. And these are very useful in probing some of the more curious parts of stellar evolution. For example, the thermally pulsating asymptotic giant branch. I'm showing here these synthetic population models by Claudia Marston from her 2005 paper. These synthesized models contain groups of integrated spectra of stars that are coeval. This is the same age and the same metallicity, except for the integrated spectra here at the top includes the thermal pulsating AGB phase in stellar evolution, and this one at the bottom does not include it. And what you see is that the infrared is a very important, it hosts very important bands of these molecules like titanium oxide, carbon-2, H2O, that will be very useful in probing how galaxies change over time and how the populations inside of galaxies change over time. So the infrared is a very unique region in modeling this sort of thing. But especially given the explosion of exoplanets that have been discovered, these are planets around other stars, we're now on the hunt for planets that may host life or may have signatures of life. Using our sample size of 1, we know that the infrared is probably going to be a very important region to look for signatures in these objects. What I'm showing here is the infrared Earth-shine spectrum from Turnbull 2006, when this is just the reflectance of the Earth's shadow on the moon. And what you see is in the infrared, there are lots of signatures that we associate with life that are visible in the infrared. So all of the missions that are currently looking for these biosignature gases are looking in the infrared, and all of the future missions are also going to be looking in the infrared to try to isolate these features. But I want to make a brief aside about these infrared molecules. Earlier this month, the APS released this month in physics history, and I learned about a little known infrared spectroscopist. His name was Elmer Imes, and he actually provided the first accurate spacing between atoms and molecules. He actually grew up in Memphis, Tennessee, which ironically is actually where I grew up, where I was born. And he got his PhD, being the second African American to get a PhD in physics in the United States at University of Michigan, studying these diatomic molecules in the infrared. being contemporaneous with Huggins, he probably used these thermal piles to do the study. And I just wanted to highlight this work because he's someone I didn't know about. And I think everyone should know about this work. And it's no doubt that the work that he did in applying this quantum theory to molecules and detecting them in the infrared definitely impacts a lot of the work that we do now in the infrared. Well, so I started this talk introducing you to something called a thermal pile, which you guys may have never heard of. So what happened to them? Well, after World War II, this cell called a lead sulfide cell took over the scene. This was developed by R.J. Cashman, and this was a very big breakthrough in infrared astronomy. All of a sudden, we go from detecting thermal radiation in the sense of detecting temperature changes to actually now trying to detect photons. And these cells really knocked thermal piles and thermocouples out because they were way more reliable. And they also had a really big increase in the sensitivity of them. By some counts and some records, 3 orders of magnitude more sensitive than the thermocouples and thermal piles. And this lead sulfide cell is a semiconductor, which really revolutionized astronomy. And we're probably all familiar with semiconductors now because they're in all of our devices and we interact with them regularly, but they occupy this special space in between metals where the electrons in these materials can flow freely, and between insulators where electrons are held very tight around their atomic nuclei. These semiconductors, the electrons are allowed to jump from this group, this overlapping of electron wave functions in this ground state, if they acquire an energy that's equal to or greater than this band gap that's shown in this energy diagram here. It turns out for lead sulfide that band gap is about 0.37 EV. And that ends up corresponding to a wavelength of a photon that is longer or shorter than about 3.4, 3.5 microns. So lead sulfide is very sensitive all the way up to 3.5 microns. And this is why it became a really revolutionary material to use in detectors. And actually, some of the first science to be done with these lead sulfide cells was done at McDonald Observatory by a name that's probably very familiar, Kuiper here. And what I'm showing here are actually strip charts. I don't know if anyone in this crowd has ever taken strip chart spectra of objects, but I was really surprised to see this in the paper, so I thought I would highlight it. These 3 spectra are actually of runs of the sun. And you can actually see evidence of the atmosphere here as things peter out and drop off around 2 microns. And there's also this other spectrum here. I would like people to hazard a guess what object that spectrum may be of. Any guesses? Vega? Vega? No. Any other guesses?
Planet.
Yes, planet. Good. Do you have a guess of which planet? No, well, close enough. It's actually Venus. So they actually, one of the beginning of doing a lot of infrared astronomy focuses on solar system objects. And so some of the first things that they do are get spectra of the sun and the planets. And this is an example of one of the first infrared planetary spectra with these lead sulfide cells. Now, after lead sulfide came on the scene, infrared astronomy did kind of come into its own. You get this infrared magnitude system that we're all very familiar with and created by Howard Johnson. You start getting the J, K, L, and M band. You'll notice that H band is missing. That actually gets added later by I think Becklin, one of the graduate students of some of the founders in this. All right, so we get our magnitude system I was telling you about. We also get the first all-sky survey that's done in the infrared. And it's called the 2 micron sky survey, but you should not mistake it with 2MASS. This survey was done by Caltech, and what they did is use one of these lead sulfide arrays and map out the sky, looking for things that may have been missed by other surveys with less sensitive arrays. And one of the things that they found is that a lot of stars had these infrared excesses, and these infrared excesses actually ended up spurring the scientific model that they are enshrouded in these dust shells. And it's neat that the SPEAR instrument on a VLT actually imaged now one of these systems that was found from this 2-micron sky survey. It's the VY Canis Majoris, which is this red, like hyper supergiant thing that's shown here. So the introduction of these lead sulfide cells really spurred infrared astronomy along. Now, I mentioned when I transferred from thermopiles to lead sulfide that they happened after World War II. It actually turns out the wartime efforts actually drove a lot of this lead sulfide development. The Germans and the Allies were actually looking at ways to develop night vision. So that was the strong impetus behind developing these lead sulfide cells. But I think the astronomers took over with this lead sulfide development. Did something that's a little bit even more impressive than looking across enemy lines. What they managed to do was actually look across the Milky Way through all the dust to actually start to map out the center of the Milky Way. Now, there's an interesting story about this happening because it didn't happen right when lead sulfide cells became popular. It ended up happening a couple years later because originally the astronomers, Noga Bauer and his collaborators, got the proposed units for the center of the Milky Way, which was still kind of speculative at the time, but the coordinates were not processed. So they were looking in completely the wrong place, and they weren't looking at a big enough swath of the sky. So it turns out his graduate student actually went back and got newer coordinates, and in their first run, they actually managed to map out the center of the Milky Way. And this was kind of the fruition of some things that a lot of astronomers, including Whitford at Wisconsin, had postulated, that if you use infrared radiation, you should be able to see through all the dust in the Milky Way to image the center. And in the end of the 60s, they actually managed to do that with these lead sulfide cells. Now, the real game changer, which was mentioned actually in the last talk that Vivian gave, was what is on this satellite right here, which is the IRAS mission. The IRAS mission was the first all-sky survey done in the infrared, and this is an example of it from Aladdin. And right around this time is where a lot of active infrared astronomy was developed. And at this point, we now start seeing completely different semiconductor architectures being used in astronomy. In particular, it was interesting to look at one of these detector workshop proceedings to see how varied the arrays were and how the sizes had all of a sudden exploded in the 1980s. You see here now, instead of just lead sulfide, now you have these new materials. You have mercurium cadmium telluride, or mercat telluride. You have indium antimonide, or we call it INSB. You have silicon indium, silicon gallium, silicon bismuth, silicon arsenide, and some of those names are probably still very familiar to people who work on detectors now. Something I want you to also notice is by the 80s, instead of having these 1D arrays of detectors, you start to have these two-dimensional arrays. And you also have another big increase in sensitivity. And this increase in sensitivity is really what keeps driving astronomy forward and actually makes spectroscopy possible. Because before it was just prohibitively expensive to do spectroscopy. And this is also another chart from that proceeding by Gabal in 1987 that I thought is really interesting. He had this metric that he was using to kind of take the temperature of the field of infrared astronomy. And you'll see some very famous data points here, like when IRTF, UCURT come online, and then you have IRAS. And he had this extrapolation for like how infrared astronomy is going to be exploding past today. Well, so this like ends in 1990. Now we're in 2017. If I had to extrapolate his line, it would be somewhere like up there. I'm not sure in those units where we are now, but infrared astronomy is certainly now like a main staple in any astronomy that you do. And some of the, at the end of that era, like at the end of the 80s, you start to do spectroscopy on objects. They're bright objects, but you finally start seeing a wider band spectroscopy. This is just an example of the spectroscopy of a quasar. And this is looking at the H alpha line of the quasar that's been redshifted into this K-band region. And this was actually being used by Morewood to probe whether the inner sides of these CFR2 galaxies, if you can penetrate through the dust with the infrared radiation, if they're actually the same as these CFR1 type galaxies. And these are the types of science questions that we are still asking and working on today. And they started right at the onset of all of this new detector architecture. And this highlights another one of the really cool parts about working in the infrared. As objects get farther away from us, cosmological redshift shifts their UV and visible radiation into the infrared. So if you want to look at objects that are very far away and do these studies where we see how things change with cosmological time, you have to start using redder wavelengths, which is what the infrared is good for. Now, at the end of the, there we go again. At the end of the 90s, at the end of the 90s, we start getting other surveys. You had a 2-mass survey that I mentioned before. You have Spitzer, which is launched, which kind of revolutionizes doing infrared astronomy. And then you also have WISE in 2009. And so now today, there are infrared instruments all over the world on the ground. This is representing Hawaii. This is the Keck telescope. You have instruments like Mosby and NIRSPEC. We heard about OSIRIS. This is the LBTO in Arizona. You got Lucy LMNIRCam. You have Gemini South here representing Chile. There's other telescopes, all that have these infrared instruments. And even at the Grand Canary Island telescope, you have infrared instrumentation. So infrared instrumentation is all over the world. And of course, it's also in space. We ended up getting a new infrared camera on Hubble. That's the Wide Field Camera 3. And you also had Herschel that was launched, and that actually probed even redder wavelengths, the far infrared and the sub-millimeter. These instruments have been instrumental to all of the advances. And of course, there's going to be more IR instruments. We're all familiar with the James Webb Space Telescope. And Vivian talked a little bit about the types of infrared instruments that are going to be in that telescope. It'll have 4. There's NIRCam, NIRSPEC, MIRI, and NIRIS. And there's also going to be WFIRST, which is going to be a wide field surveying instrument. But it's also going to have a coronagraph to start probing around some of these planetary systems that we're interested in the infrared. Now, all of these systems use now a modern architecture of detectors. And these detectors are now much bigger than what they were before. Instead of these 330 by 30 or 60 by 60 systems, we now have 2K by 2K systems, and now we're even moving to 4K by 4K systems. They also have incredibly low dark current. I'll just flip back to this old slide here from the end of the 80s. You can see the dark current measurements that they have for these arrays. If you look at Mercat Telluride, it was around 800 electrons per second per pixel. Nowadays, we hover around 0.01 electrons per second per pixel, and we're trying to get better than that, as low as you could possibly get. So there's been lots of advances for the current architectures. And these current arrays make new studies in the galaxy evolution and star formation possible. This is just an example of one where we're looking at these spectra taken from the GNIRS instrument on Gemini, where you're looking at these nearby galaxies, near-infrared spectra. And what Riffel et al. Did was look at how the stellar population models that include these evolutionary stages like thermally pulsating AGB stars and other evolved states actually match up to real data. And the punchline was they kind of fit, but you still need more information. We still need more data. We have to include more evolved stars, and none of the models predict the infrared of these galaxies completely correctly. So we still need more data in the infrared on stars and on galaxy to drive things forward. We even have exoplanetary atmosphere spectra. Of course, these spectra are very particular. They're of hot Jupiters. So these spectra have all been taken using the Wide Field Camera 3 on Hubble. This is using a very similar method that Andrew talked about earlier, where you're using the star's light passing through the atmosphere of the planet as it's in transit. And what Iyer et al. Have done in this plot is actually plot up a representative, it's kind of like an average spectrum of a water feature that they've discovered around these hot Jupiter type planets. And this is something that we couldn't even predict that this wide field camera and this near-infrared grism will be used for on Hubble, but it's kind of exploded this field of looking at exoplanetary atmospheres and looking for things like water and other biosignatures. Of course, here, these are hot Jupiters, so these are really just probing these big puffy atmospheres and whether they have clouds and hazes. But in principle, we want to do this sort of thing for exoplanets or terrestrial-sized planets. And to do that, you need this future instrumentation that got briefly mentioned in some of these earlier talks. There are two mission studies going on, LUVOIR, Large UV Optical Infrared Telescope, and HabEx, that are both going to be looking for getting these very faint signals of exoplanetary atmospheres and actually getting spectra of them. And up here you have the image of the LUVOIR rendering, and down here is HabEx. And what you have here in this plot is from the HDST Aura report. You're actually seeing the relative flux of the planet's flux to the star's flux. I'll draw your attention to that. This is 10 to the minus 10 scale factor here. So the signals that we are probing now are extremely faint. And you have to overcome the central star also to actually even probe these faint signals. So you have to use coronagraphs or star shades or combinations of these things. And what I'll draw your attention to is that here's a really cool, pretty looking spectra, but that's a warm Neptune. Those features are very easy to identify. But if you actually look at what Earth looks like, it's this little scraggly line down here. So things are getting very difficult to do exoplanet spectroscopy of Earth-like planets. And this increased sensitivity that we want to do all of these new missions is creating friction between the development of our near-infrared instrumentation. Something you always have to worry about in near-infrared instrumentation is the thermal background. Even from the beginning, astronomers discovered that you had to submerge your cells or your arrays in liquid nitrogen or other things to get down a background and to increase your sensitivity. Today we have cryostats. It's very easy to cool down optics, or relatively easy. And for things like the LUVOIR mission, if I go back here, you can employ things like star shades to kind of keep a thermal background down low. So thermal background is an issue that we think is probably mostly handled when we're doing infrared astronomy now. There are two very pesky options that remain, though, that are the fields of active research and instrumentation with infrared. One is persistence, and the other is read noise. So persistence, if you've never seen it or heard of it, is this appearance of signal from a previous exposure and your current exposure. And this is an example of it from the Lucy instrument on the LBT. What you see here is a spot from a star, and then this is a slit view. What you see on this right side here is now we're looking at taking science data. Before it was calibration data. Now it's science data. And you see your science spectrum, but you also still have this faint signal of the slit view and this one spot. I think that was a star. So as you can imagine, if you're doing very sensitive measurements that involve doing photometry or spectrophotometry, worrying about the excess signal from previous exposures in your current signal is going to throw a wrench and lots of reduction and lots of calibration. And it's essentially going to raise your sensitivity floor. Now, there's a current theory out in the detector world that we understand persistence being charges that get trapped inside of these impurities inside of a photodiode. And I'll kind of walk you through the model that we have. A lot of the arrays that we use now are Mercat Telluride. These are sold by Teledyne. They're readily available. And this is a model for one of these photodiodes. So this whole pair here is considered a pixel. What we do with these photodiodes is we actually reverse bias them so that what you have in the center region is this undepleted zone of charge carriers. And there's an electric field that once a photon comes in and creates this pair of hole and electron, a hole is just the absence of an electron, this electric field sweeps the charge into these opposite ends of these. There's like a cathode here that's charging this up. So it sweeps to opposite ends. The depletion region here that was free of charge shrinks. And that's your signal. This shrinking of your depletion region is your actual signal. Well, when you go to reset your array to restore that reverse bias, what we think persistence is that some traps that were not completely freed, or that were some traps that held charge that didn't go all the way to the ends get freed up once you apply this new electric field. So things that should have been detected as signal now get detected signal in the second frame after your reset. And because they have the same polarity, these little minus signs, these electrons going here, the holes going there, it gets masqueraded as a signal. What a lot of Roger Smith's work did show, though, was that there seemed to be characteristic time scales for this sort of decaying back into these non-depleted regions. And so lots of people, myself included, started doing tests in labs where we tried to characterize this persistence, try to measure it, measure out the time scales in hopes of correcting this persistence. And the tests are very simple, deceivingly simple, but it'll get more complicated as I'll explain later. You reset your array and you just take an image with a flat field or with some light source on, and then you just reset the array, and then you just take another set of images with the array dark. In this dark frame, you should be able to see any charge that's going to be created as persistence. And that's actually what you see here. This is real data from when I was at University of Wisconsin. At time 0, there's no charge being released because we just reset. But what you're seeing here is the accumulation of charge in a completely dark frame, not a frame with signal, but a completely dark frame. And you see that an exponential actually fits this data really well. But when you're taking science data at a telescope, you're not just taking a picture of one field and then going completely dark. What you're actually doing is moving from field to field with stars that range in fluxes, and you're having different exposure times at each of those fields. So useful tests to do are also using consecutive signals, not just doing one signal, look at a dark and see how the persistence decays. You actually want to see how does the relative flux between signals actually affect this decay. And it turns out the answer is it's complicated. The persistence in that very simple regime of, hey, let's take a bright image, now let's take a dark, is actually very straightforward. This is an example of a persistence frame. So this is not a signal frame. This is actually a persistence frame that I reduced from Hawaii to our G array while I was at Wisconsin. Using those decay parameters that you can get from the test data, so the time scale of decay, you can correct your data. This is a pretty good correction. The persistence in this frame, I think, is on the order of 10% or less. So it works fine in the limited regime of you're taking a very dark exposure. But the reality is, when you try to apply the decay curve methodology to data that's not in a very simple controlled environment, it doesn't work. It's not so easy. It's very nonlinear. And the problem is that persistence very much depends on the signal that creates persistence. Then it depends on your exposure time. And then it also depends on the relative signal. So there's lots of factors that go into trying to characterize persistence. So if you want to make a data set to actually characterize persistence in your array, the data sets become huge, and the amount of time you have to spend taking data starts to become very daunting, and it becomes unmanageable. People are still working on this today. I know of a group at ESO that's actually doing detailed studies on arrays to try to figure out clever ways to characterize persistence with reduced data sets, but it's a tricky thing to get over. The good news, and there's like an asterisk here, is that with the WFIRST project, actually, they've been finding that they are able to reduce the persistence in their arrays by changing how the arrays are made altogether. So this solution is essentially, you can get better persistence if you just buy new arrays. It's been shown that the persistence in different arrays varies, but if you want to get better persistence, it has been shown that these manufacturers like Teledyne can actually make arrays that have less persistence. But it's their special recipe, and that does mean $, more money. You have to buy other arrays or request a specific type of array. So this persistence problem is not going to go away anytime soon, and we're actively working on how do you characterize it, what's the physical model behind it, and can we get rid of it completely? Now I mentioned read noise as this second barrier. This is a chart from that HDST report. And what I want to draw your attention to is the near-infrared column here, the band. And you see a lot of the strongest driver on the technology here in the infrared are the exoplanet science domain. Infrared is also going to be useful in these other science domains. But in the infrared, it's the most stringent constraints. We want to obtain spectra and get biosignatures, and we want to characterize planetary systems. And when you look at the detector requirement, you see here it says PC. It doesn't mean politically correct. That is photon counting. So right now, when we do arrays, and this is where we actually use multiple sampling, like we do Fowler sampling, the best we're getting down to is like 5 to 6 electrons. So nowhere near photon counting yet. So there's a lot of work that needs to happen with near-infrared arrays to get to this photon counting regime. And one of the things that I'm actually working on is at Goddard, we're building a small test bed to actually inspect and detail an H4RG array. Right here, we're controlling it with a leash controller. There's no detector in this picture. This is just a setup of the bench. But we're going to be probing the entire signal chain, looking for what types of noise comes in at every stage of the detection with the running array. So we're going to be looking at figuring out where the dominant noise sources are and how we can minimize those noise sources with potential advancements in readout, circuitry, or other variables that may affect detection. And actually, I have here, this is my first light instrument, one of these H4RGs. It's not really a first light instrument. This is actually taken at room temperature, and this is a difference frame. So it's not very interesting. Working on the detectors and the noise characteristics, you really don't get to look at very pretty images. This image, though, was proof that, like, hey, we could turn on the array, and we have the array working. We're going to use this setup. Right now, we're focusing on read noise stuff and just getting the array built up. But we're going to also use this array to test persistence. We have integrating spheres that we're going to put different infrared wavelength light in and actually try to probe some of the detailed characteristics of persistence and actually do some experiments to see if we can replicate some kind of anecdotal results of people being able to eliminate persistence with different procedures. But I've been talking mostly about these Mercat Telluride arrays before. These are the Hawaii H2 and H4RG arrays. But something that's coming on the scene very quickly and very recently are these electron-injected avalanche photodiodes. And you all may have never heard of those before, but these are crucial little components in AO systems. Right now, people use these avalanche photodiode cameras, and these are pretty small arrays usually, to read out very quickly images of stars that are jittering or moving around on the sky. So they've been very good at driving AO systems, and very good if you're doing near-infrared interferometry at tracking fringes. But Gert Finger and his collaborators over at ESO are actually trying to experiment with adapting some of these avalanche photodiode arrays to work in these low light, faint infrared spectroscopy or imaging ranges. And actually what he's shown here, this was at the SPIE meeting in 2016, is results from taking images with these arrays. These images are extremely short, in some cases less than a microsecond frames, and then doing Fowler sampling of these frames. And what you actually see in this is that if you look at the skeleton axis, this is the readout noise that they're measuring. This is where one is right here. This is one electron. And they're actually measuring if they can do these multiple sampling techniques, getting down to sub-electron read noise levels. But if you're scratching your head thinking, this must be too good to be true, you're somewhat right. These arrays, these really small arrays, read out very quickly. And there's a huge amount of dark current that starts to get injected in these systems. So dark current is the price you pay for these arrays, reading them out very quickly and trying to get these very low read noises. So there's no free lunch yet, but I think these arrays are probably an interesting alternative that are slowly emerging to maybe boost infrared astronomy up the next level into the photon counting regime. We just have to figure out how to get dark current down. So hopefully I've taken you on like a little tour of how infrared astronomy has developed over the years. We've come a long way from these lead sulfide cells to these now massive arrays of these Mercat telluride photodiodes. And it's unclear at this point, what is going to be the next big advance in detectors. Is going to be these avalanche photodiodes, or is it going to be something that's more classical that's been proposed, like that are more like bolometers, things that are really sensitive to tiny temperature changes that can do really detailed work. But I think the one thing that'll be clear is that it's definitely going to be exciting, because whenever we have these breakthroughs in technology, we always go out and look at the sky and find things that are unexpected or surprising. And that just keeps pushing the science that we can do forward even more. So, all right, I'll stop there. Thanks.
All right, any questions? We'll go ahead and start here.
Just for a real quick perspective, could you contrast the characteristics of your Mercat telluride arrays with a modern, well-developed optical CCD system?
So the modern optical CCD systems are routinely getting read noises of order like 2 electrons. Whereas in infrared, like I said, we can get down to 5 to 6 electrons, but you do Fowler sampling, essentially. Persistence is not as big a problem in these CCDs, but there are effects that when people are starting to use these more sophisticated technologies, like EM CCDs, there are effects that are becoming more prominent. Yeah.
Yeah, all right. So I have a quick question. We talked a little bit about read noise.
Yeah.
But does read noise ever change across the detector?
The answer is yes. Often when we quote read noise for arrays, it's the quick and dirty way where you do kind of an average or a median over the entire array. But most certainly the read noise changes across the array. And when you're trying to identify bad pixels and good pixels, those read noise maps are like crucial. So yeah, it definitely changes across the array. Yeah.
Cool. All right, any more questions? I have one.
Yes.
So you talked about the exponential decay.
Yes.
And then you mentioned that the best test is to have a different scenario of like exposure to light twice.
Yes.
And then a break and then again.
Yes.
So is it just exponentials added together? Do you know the answer yet?
Yeah, so the first example of doing the test like that was done by Roger Smith, and he did find that, it seems to fit well, that it seems like a superposition of exponentials. I did like a similar test. It was different. I wasn't testing changes in fluxes. I was testing changes in exposure time, and I actually found that it was not that simple. It was not just a kind of overlaying of exponentials, that something more complicated is going on. So I think the answer is it depends, which is an unfulfilling answer, but yeah.
Great. Well, let's go ahead and thank Greg again. And next up we have